In this graph, we're going to look at our method for finding area in polar graphs. And so I'm going to start out with a generic polar graph, something like this. And R here is some function of theta, theta being our independent variable, and R being the dependent variable. And I want to find the area between this angle, which I will call alpha, and this angle, which I'm going to call beta. So I want the area in between those angles, which if you think about rectangular area, we usually find the area between two x values. Here we're finding the area between two theta values because theta is our independent variable. And so I'm looking for this area here. Now in rectangular coordinates, when we're finding area, we talk about it as area between the curve and the x-axis. Obviously, that doesn't make sense here, but when we're finding area in polar graphs, we're going to find the area between the curve and the pole, starting at one angle theta and stopping at another angle theta. Also, with rectangular area, if you remember when we were calculating that area, what we were actually doing is summing up the area of infinitely many rectangles using an integral. And we're going to use that same notion here, but instead of summing up rectangles, because that's not going to work with this kind of region, what we're going to do is sum up infinitely many sectors. And so I'm going to draw in one sector here. And hopefully you can imagine if that was infinitely small and we had infinitely many of them, starting at alpha and going to beta, they would fill in that area. We could sum them all up and find the area of this region. So to get our the formula that we're going to use for polar area, let's think about a sector. And I'm going to start with a circle. It's a pretty round circle there for freehand. And I'm going to draw in a sector. Do a little geometry review here. So I'm going to call this angle here, I'm going to call it delta theta, a change in theta, whatever the change is from this angle to this angle, delta theta. And if you remember, a sector is, we're going to think about the sector just as a fraction of the circle. And so the area of the entire circle, of course, is pi r squared, but we just want a fraction of that. So we're going to multiply this times whatever that delta theta is over 2 pi, because 2 pi would be the complete circle. And we just want the portion that's represented here in this sector. And so this would be the formula for area of this one sector. Now, notice in our formula here, since we're using radians, our pi's can cancel out. And so this simplifies down to, I'm going to kind of rearrange, and I think you'll see why I'm doing this in a moment. We have 1/2 left here, the r squared, and then I'm putting the delta theta at the end. So if this formula here gives me the area of this representative sector, which it does, that's the formula for the area of a sector, we can sum up infinitely many of these. If we do infinitely many, of course, we want that delta theta to become infinitely small. We want it to become a d theta. And we're going to sum up 1/2 r squared d theta, starting at our angle alpha and going to our angle beta. And so this is the formula that we're going to use to find area within or area between a polar graph and the pole between two theta values. So let's look at an example. We're going to start off with r equal to 2 plus 2 cosine theta. And we just want to find the area in the interior of this whole curve. Now, we learned how to graph these curves, and you can sketch a graph if you want to, but if you don't need it, you don't have to. One of the main reasons I went through how to sketch these graphs is so that we understand how polar graphing works. If you recognize this formula, this is going to graph a cardioid. And so if we want the area of the interior, we can just integrate this using our area formula, starting at 0 and stopping at 2 pi. And I got a little bit ahead of myself there. That is one of the biggest challenges with polar graphing, is determining what theta to start at and what theta to end at. So I'm going to go ahead and just sketch this quickly. 2 plus 2 cosine theta, that's going to be out here at 4. It's going to cross here at 2 and 2. And this curve is going to look something like this. Not the best cardioid I've ever drawn, but we get the idea. And it does start at 0, and it goes all the way to 2 pi we get down. So if I want the area of this whole entire region, those are the two angles where I'm starting and stopping. And so to find the area, it's going to be equal to the area from 0 to 2 pi, 1/2 r squared, and this is my r, 2 plus 2 cosine theta squared d theta. And then this is an area that you could determine on a calculator. It can be done by hand. It involves the use of some trig identities, and I will say typically on the AP exam, we're not expected to do these integrals by hand. So we could do this on the calculator, but for the purposes of our examples, I'm just going to find the integral and leave it there. Now, one of the main challenges of finding area with polar graphs is knowing where to start and where to stop. One of the other interesting things about polar graphs is that because of the symmetry that happens, there are multiple integrals that we could use to find the area inside this curve. Another thing I could do is start at theta equal to 0 and stop here where theta is equal to pi, integrate from 0 to pi, 1/2 2 plus 2 cosine theta squared d theta. That, of course, would give me the area of the top half of this curve. And so then I could just multiply that by 2, and that's going to give me the same answer as the first integral that we wrote. And so that's something that you have to watch out for, is just different ways of writing the integral that's going to result in the same answer. Okay, for our next example, let's look at r equal to 4 sine 3 theta. And hopefully you recognize that equation is one that's going to graph a rose curve. And so we want to find the area inside one petal of the curve. Find the area inside one petal of that rose curve. Now, this is why I taught you how to graph in the way that I did, because for me, I think on one like this, finding the area inside one petal, again, the important thing is going to be determining where the petal begins and where it ends. What theta am I starting at? What theta am I stopping at? And I think this graph is easier sketched in a rectangular form, and I think it's also easier to determine where the petals begin and end in that rectangular form. So if I sketch this graph, my amplitude is 4, so we're going to go up to 4 and -4. There's no vertical shift, so my midline is the x-axis at 0. The period here, period is equal to 2 pi divided by 3. And so by the time I get to 2 pi, I should have 3 cycles of sine. So 2 pi over 3, 4 pi over 3, and 2 pi. I may be wishing I had made this graph bigger, but we're going to go with it. So I need to get a full cycle of sine done by 2 pi over 3. So there we go. I made it fit. It's a little skinny, but still work. Okay, so this is what our graph looks like. And if you remember from when we learned how to sketch these graphs, one petal of the curve is going to be like basically this part right here. And so what I need to know is where does that petal begin and end? And I chose that one just because it was the first one. We could pick any of these sections and it would give us one petal. So this, obviously, the petal that I chose starts at 0 and it stops halfway from 0 to 2 pi over 3, which of course would be at 1 pi over 3. And so this area is going to be equal to the integral from 0 to pi over 3, 1/2 r squared d theta. Again, the challenge here being figuring out the theta where you begin and where you end. 1/2 4 sine 3 theta squared d theta. Now I'm going to do one final example, and this is the same r that we looked at before, but this time I want the area of all the interior of the curve. This is where it's really important to understand how these graphs work. If you remember, whenever the coefficient on our theta was odd, then the number of petals on the graph is equal to 3. If that number was even, then the number of petals on the flower is double. And if you remember what happened when we graphed this, we graphed from 0 to pi and it completed the rose curve. And then as we went from pi to 2 pi, we just graphed again on top of the curve. So there were actually 6 petals, but they were on top of each other. And so understanding that is really important, because if it says find the area of the interior of the curve, you might think, oh, well, we can just integrate from 0 to 2 pi. That'll give me, all the area inside the curve. But actually, in this case, that would give me double the area. And so if we understand that, if we remember that, then we know we can graph from 0 to pi, 1/2 r squared d theta. And that's going to give me the interior of this particular curve, because by the time I get to pi, I have finished graphing the rose curve. Another way we could do this is if we know this curve has 3 petals. In the previous example, we found that this is the area of one petal. We could just take that same integral and multiply it by 3. So area is equal to the integral from 0 to pi over 3, 1/2 r squared d theta. And we just multiply that by 3. That's going to give me the area of the entire rose curve. Again, showing that there can be multiple ways to find the area of the same polar curve.